All right, Amperes Law. So here we go. Use the black at the beginning. So Amperes Law. It is, well, this is what it is. So it's b.dl, along some path, but the path has to be a closed loop, equals mu naught times I enclosed. So, and this is one of the Maxwell's equations. Let's try to understand what this equation actually says. And I'm not going to derive this equation, I'm just stating it. And I'm going to teach you how to use it. Now, suppose you have a magnetic field that points in a certain direction, and that this magnetic field is produced by a current. So let's say you have a current that flows like this current I, and then this current I sets up a magnetic field. The magnetic field points would be easy to figure out. Given the right-hand rule, you would point your thumb in this direction and then curl your finger, so the magnetic field here would just be would do something like this. And maybe something like this. All right, here we go. So this is the magnetic field. And what this says is that if you were to throw a certain path, any path whatsoever, as long as the path is closed. So maybe you start here and then you roam around and roam around and roam around and go like this, and here you end up back the same spot. You have to close this path. This has to be a closed loop, so this has to be closed loop. Just in case you're wondering, this is not a closed loop. This is not a closed loop. This is not a closed loop. But if I were to do this here and close it, that'd be a closed loop. If I were to do this and close it up, that's a closed loop. And if I were to do this here, that would now be a closed loop. Anyway, so so you need to have a closed loop. That's what that equation says. And let's see what else we can do with it. So now you go and you move around this loop like that. You set this loop up and you add all of the little magnetic fields with this path dl. So maybe here you have a little path dl that points like this. And at this point you have some magnetic field that points in, let's change the color. At this point you have a magnetic field that points in this direction here. So there's some magnetic field B here. Now you move on, and then somewhere here at this point you have magnetic field that points like that. So here's B, and at this point you have a little bit of the path dl that points like this. And you keep multiplying these, so maybe here you have a path segment dl, and you have a magnetic field, and the magnetic field, let me change the color. And the magnetic field here points maybe like this. So here's magnetic field B, and then maybe somewhere here at this point the magnetic field points more like this, while the dl element points like this, always tangent to the path you take, and so on and so forth. You complete this, you multiply all of these out. So this is the left hand side. You choose path, any path whatsoever, as long as it is a closed path. And then you multiply dl times b at every single point along this path. That's the left-hand side of the equation. Turns out that when you do that, all of that will always equal to the a constant mu naught times the current enclosed. Now, current enclosed by what? The current enclosed by the path you chose. By the path you chose. So this loop here, dl. And so in this specific case, there's only one current. But suppose your picture looked like this. Here's the current I, I1, and then here's another current I2, and then maybe perhaps here's another current I3 that flows like that. Here's I3, so you have 3 wires that somehow line up like this. And then your path, and they all contribute, they all set up certain magnetic field here. And let's say your path of integration looks like this. And you come back, you close the loop. So this is the path along which you're going to integrate. All of the little DLs are all over the place, right? DL, 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 and so on. And the magnetic field is present everywhere, but it is the magnetic field that is comprised of the contributions of all 3 currents. And in that case, this charge, this current enclosed would be the left-hand side. So for this specific case, you would have to do the integration here where you have B dot DL along a specific path, and it's this red path. So maybe I'll put along path, the red path, and the right-hand side would become mu naught times I1 plus I2 plus I3, because your path here encloses all of the 3 currents. Now here's a bit of a twist to the story. Suppose now that one of the currents was pointing in the reverse direction. So let's say that I2, instead of pointing in this direction, it was actually pointing in this direction, the opposite direction. So in that case, 2 currents flow into this loop and in a specific direction, and 1 current flows in the opposite direction. So you would actually have to subtract I2. Right? Another way to draw this is to draw it like this. You have this loop. So here's the loop, right? Where you have all of these little elements DL all over the place. Put one more. And then you have a current I, where here's I1. It flows into the loop. This is I1. Here's I2, which flows out of the loop. This is I2. And then here's I3, which also flows into the loop. So since I1 and I3 flow in the same direction, you can add them, but because I2 flows in the opposite direction, you would subtract it. Okay, so this is the Amperes Law. This is the overview of the Amperes Law, and this is more or less what it says. We will use this law to derive an expression for the magnetic field close to a straight wire that carries a current I. We will use this law to find the expression for the magnetic field in a solenoid where the current flows into the solenoid, and I think we're going to also do a toroid where you take the solenoid and you loop it into a circle like this, and I think we will also do a loop where the current flows in a loop. Okay,